Hello, academics. Today we're going to be learning about characteristics of polynomials. This is our second lesson in our series on advanced functions in the Ontario curriculum. So our first idea for this lesson will be about local and absolute minimums and maximums. So to display this, I'm just going to draw a few simple functions here. So our first one will be on just like this. Let's say it goes like that. We can see here these are local minimums and maximums at these 2 points because we can see the function eventually reaches a higher level than that. So here, as we can see, as it increases, this has a greater y than the point there. However, for let's say this section of the function, this point is our local maximum. And the same thing applies. That is our local minimum. So if we cut it there, we can see that is our local minimum. They're very easy to spot because they often involve a curve such as this, where we can identify the peak of that curve, even though it may later on increase. But let's continue with another example. Let's say we have the polynomial that resembles something like this. Right? These are just rough sketches, but we can see this one here has a local minimum here, a local maximum there. And you know what? Let's just modify this function to make it a little more clear. Let's say it goes like that. We can see this point is our absolute maximum, because if these two keep going down forever, the function will never reach a greater y than here. That is our maximum y. So we can see this is the absolute max, but we still have some local maximums here. So these two are still local maximums. So our next topic will be about odd degree polynomials. So that means a polynomial that has an odd degree. So for example, x power 3, or we could have, let's say, x power 5 plus half of x squared. So although 2 is even, the overall degree of the function is 5 because the highest exponent is 5. So this is still odd. And we're just going to analyze some of its behavior. So let's take, for example, something simple like this and something a little more complicated like that. So this one here is a positive leading coefficient, and this one has a negative leading coefficient. We can see that because it goes from quadrant 3 to quadrant 1, and this one here goes from quadrant 2 to quadrant 4. And we can see just overall, this one will tend to increase as time goes up, and this one will tend to decrease as time goes on. But beyond that, we can look at their local minimums and maximums. So here we got one max there, one minimum there. And this one on the right has a bunch of them because it's a higher degree function. But what we can see overall is that there is no absolute max or min. This is very clear because on both ends, our functions will just keep increasing to infinity. So that's positive infinity. This one here is negative infinity. So that means no matter what the maximum or minimum is, for example, this one could go up here and then keep going. But no matter what it is, it will never be as big as infinity. And so we know that it never has an absolute maximum because it covers both ends of the infinities. And that's the same for the negative. This side here goes to positive infinity. This side here goes to negative infinity. So no matter what the local minimums and maximums are, they will never be able to be absolute maximums on an odd degree function. But if we look at a even degree function, for example, let's say x to the power of 4, or we could have x to the 2 plus x plus 3. These are still both even because the degree is even. And so let's take, for example, here. Here we're going to draw a positive one. So let's just say a simple parabola like that. So that's positive. And this one on the right, let's draw something a little more complicated. Maybe something like that. So that's a higher degree one, but this one is negative. And we can identify our minimums and maximums. So here we got a minimum right there. This one we have a maximum, minimum, a bunch of them because again it's a higher degree function. But what we can see is this one here is the absolute minimum because nowhere on this function does it go lower. We can see that these increase to positive infinity, and on the left it also increases to positive infinity. So we can reach a minimum for the overall function right there. And the same thing can be said for this one, where we can see this right here is our highest y. So this is where our y is the highest. And so that is our absolute maximum, because both of these extend to negative infinity this time. So we can say that there will always be a absolute max or min on an even degree function, not an even function. That's a different thing, an even degree function. There will always be an absolute maximum or minimum. And there are even some special cases that the function will do something like that, where we can see that there are two local maximums that have the exact same y. That is possible. It's a little more rare, but it is possible. And so you could say they are both the absolute maximum. So the function reaches a maximum at 2 points. It's a little more rare, but something to keep in mind. But moving on, they have one thing in common, is that both at even degree or odd degree functions have up to degree minus 1 local or absolute minimums and maximums. So what this means is, for example, let's say we are given the drawing here and we have this function and we're trying to decide what it is, right? We just want to know what is the minimum degree of this function. So we're pretty much asking, what is the lowest number that the biggest exponent will have? For example, this one like that, plus let's say x2 plus x plus 3. Let's just say that, right? What is the biggest degree? That's what we're looking for. And what is the smallest value we can have? And so we'll use our equation of degree minus 1 is equal to the number of mins and maxes, right? And so the degree is equal to the number of mins and max plus 1. And so let's just count them. We got 1, 2, 3, 4, 5, 6. So we have 6 plus 1. And so our minimal degree is 7. And let's see if that's true. So here it starts in quadrant 3 and ends in 1. And in the previous video, we established this was a possible behavior for only odd degree, not even degree. And so we can say 7 does make sense because it is odd. And so we'll follow the behavior that we established up here, starting in 1 and ending diagonally. But that's it that I have for this lesson today. Thank you so much for paying attention, and feel free to check out any other videos, or if you have any questions, leave them in the comments. Thank you so much.